So this is the last one from homework. So they want us to simplify this using our identities. So for the cosine, they was singing up in there for real. So for cosine, u plus or minus v, that's cosine u, cosine v, minus or plus sine u, sine v. I was supposed to put one of those on y'all's quiz too, wasn't I? Guess that'll be y'all's quiz tomorrow. Maybe. So if this one is plus, that's the top sign here, so we need to use the top sign there. So it's minus whatever that is, and that is cosine u, cosine v, minus sine u, sine v. Then that's multiplied times cosine v. So that takes care of what comes before the minus sign. Then it's minus whatever that is. So the sine u plus or minus v, that's sine u cosine v plus or minus cosine u sine v. So if it's plus here, it's plus there. So that'll be sine u cosine v plus cosine u sine v. Then that's multiplied times sine v. So let's see. Before we multiply this out, let's bring the cosine v up here. Let's call that minus cosine v times what's in parentheses. And then let's bring the sine v here. So that's minus sine v times what's in the bracket. Sine u cosine v plus cosine u sine v. Now let's get rid of our brackets. So let's distribute. So when we multiply those, are there any common factors for multiplying? So we multiply that out, negative times cosine u, and cosine v times cosine v is cosine squared v. Think if we have x times y times x, we just change the order of those. So we've got two of those multiplied together. Well, if we multiply those three things together, we've got two cosine v's multiplied together, so cosine squared v. Then we need to distribute to there. None of those are the same. Negative times negative is positive. So that's sine u, sine v, cosine v. Now here, when we distribute, none of those are the same. This is sine v, this is sine of a different angle. U and v, sine u, sine v, those are different, so that's not sine squared. So we can just call that negative times positive is negative. Sine u, sine v, cosine v. Distribute those. Negative times positive is negative. Notice those are the same. So we have a cosine u. Sine v times sine v is sine squared v. So to start with, it's just using the identity for the sum and difference identities for sine and cosine. Now we distribute. Are there any like terms? Any terms that are alike? Notice those two middle ones are alike. What happens when we combine those? They cancel. Those are the opposite of each other, so those cancel. So that leaves us minus cosine u times cosine squared v minus cosine u times sine squared v. Do those two have anything in common? Both of those have a cosine u, and our leading coefficient is negative, so let's factor that out. If we take a minus cosine u out of that, we're left with cosine squared v. If we factor a negative out, it changes that to a positive. Take the cosine u out, and that leaves us with sine squared. And what does that part in parentheses simplify to? 1. Sine squared plus cosine squared is 1, so that's negative cosine u times 1, or minus cosine u. So we took something that was very messy. We used some identities. We distributed, combined like terms, used another identity, and got it to something that was really simple. So, for example, if we needed to evaluate that expression for 10 different angles, that would be aggravating to have to put in a u and a v, all of those places, combine things that are alike, take cosine, take sine, multiply, subtract, where really that's just equivalent to taking cosine of u and doing the opposite of it. So by simplifying that, if we had to evaluate that expression, that's equivalent to it, but that's a lot simpler to evaluate. All right, what else from 7.1? What other specific homework? 17. Something like this. All right. All right, this comes from one of our sum and difference identities. Our sum and difference identity for tangent is tangent of u plus or minus v. Let me make sure I tell you this correctly. Is tangent u plus or minus tangent v over 1 minus or plus tangent u times tangent v. So notice they give us tangent 26 degrees plus tangent 20 degrees over 1 minus tangent 26 degrees tangent 20 degrees. So they're giving us the right side, and what is u? 26 is u. What's v? 20. Let's see, they're using a plus here, so that means use the top sign here. They're using a minus here, so that's the top sign here. So if we use the top signs on the right, we have to use the top signs on the left. So that means that's equivalent to tangent of 26 degrees plus 20 degrees. So that's equivalent to tangent 46 degrees. So they say, put that in, do not include the degree symbol in your answer. So tangent 46. Then they want us to evaluate that. So tangent 46, that's not a special angle. So if we take 46 degrees, take tangent of it, if we round that to 4 decimal places, 1.0355. 1.0355. And that's all they wanted us to do. So they just wanted us to recognize, hey, that was a sum or difference identity for tangent. And which part's U, which part's V, and do we do plus or do we do minus? All right, any more of those specific out of 7.1? Anything? Well, if you work through some more of those and there are more that you're having trouble with, then you can ask about those tomorrow. But I guess today we can go ahead and look at the next section. 7.2 just picks up where we left off. It just adds some more identities. So let me pull this up in the book. On page 507, they list the cofunction identities, and these should look somewhat familiar. The only difference is the way they're listed here has our angles in radians, and when we looked at these previously, we used angles in degrees. So if we look at the bottom here, we've done these before, but in the past when we wrote them, we said sine of 90 degrees minus x equals cosine x. And what that meant is if we know sine of an angle, that's equivalent to cosine of that angle's complement. Remember, complements are angles that add up to 90 degrees. So if we know sine of 40, then sine of 90 minus 40, so actually I said that wrong. If we know cosine of 40, that's the same thing as sine of 90 minus 40, sine of 50. If we know cosine of 70, that's the same thing as sine of 20. Now it works the other way also, using this one. If we know sine of an angle, that's the same thing as cosine of its complement. The only difference between this and this is our angles are listed in radians instead of degrees. So we've had these identities before, we just had them in degree form instead of radians. But pi has 90 degrees, those things are equivalent. Well, the next page, 508, there's another set of identities that take those and flip them around. So, well, what if we have the angle first and then minus pi halves or plus pi halves? We don't run across these very much, so I don't emphasize these. If you happen to run across these, then just look up the identity. This is them. But the ones we need to be more familiar with are those. We can actually get these by combining those with what we talked about on our quiz today, that is the same thing as minus sine x, and that's the same thing as cosine x. So if we take our angle and flip it around, so if we take that and flip it, how does that impact it? Well, that gives us the opposite. We take that, take the opposite, so we take that and flip it, well, it gives us the opposite. But again, those we don't emphasize very much. What we want to spend more time emphasizing are the double angle identities. So what I want you to do for tomorrow, I want to include the sum and difference identities that I didn't quiz you on today. They were in 7.1. And I also want to include the double angle identities for quiz tomorrow. And we'll throw those cofunctions in there, the first set, not the second set. So double angle, sum and difference, and cofunction. So know those three sets of identities for a quiz tomorrow. So the first double angle identity, sine of 2x, that can actually come from the sum and difference identity. If we have sine of an angle plus that same angle, what's x plus x the same thing as? 2x. X times x is x squared, x plus x is 2x. Well, remember our sum and difference identity for sine said take sine of the first angle times cosine of the second angle. If this is plus, do a plus here. Cosine of the first angle, sine of the second angle. Well, notice those two things are the same. Sine x cosine x, sine x cosine x. So sine of twice an angle is 2 sine x cosine x. So you're not going to have to know how to generate that identity. You just need to know. But that's where it comes from. Same thing with cosine 2x. Cosine of 2x is the same thing as cosine x plus x. So if we apply our sum and difference identity, that's cosine of the first angle times cosine of the second angle. If this is a plus, we put a minus here and take sine of both angles. So cosine of twice an angle, cosine times cosine is cosine squared. Sine times sine is sine squared. Now it turns out that if you look in your book, look at the ebook online, they actually give us 3 different versions of cosine 2x. Remember the first Pythagorean identity? Sine squared plus cosine squared equals 1. If we isolated, let's say, cosine squared, we could subtract sine squared from both sides. And if we replaced cosine squared with that value, we would get 1 minus 2 sine squareds. Or if we isolated sine squared is the same thing as 1 minus cosine squared. Substituted that in place of sine squared, we would get 2 cosine squared minus 1. So all 3 of these are equivalent to cosine of 2x. This is kind of the standard cosine 2x. But sometimes when we take cosine 2x and replace it, we only want either sines or just cosines. So if we want just sines, we would use this version. If we wanted to replace cosine 2x with just cosines, we would use this version. But all three of those are equivalent. And again, you don't have to know where they come from necessarily, but one thing I get confused on sometimes is the one that has 2 sine squared, is it 1 minus 2 sine squared, or is it 2 sine squared minus 1? But if we think about, this comes from replacing cosine squared with this, we would have 1 minus sine squared, so 1 minus 2 different sine squares. Same thing with this one, if we took sine squared and replaced it with this, we would have cosine squared minus 1 minus cosine squared, so we would have 2 cosine squareds and a minus 1. For tangent squared, or tangent 2x, we don't use it as frequently. But you could get it the same way. If you take tangent u plus or minus v and let both angles be x, cosine x plus x is cosine 2x. So you'd have 2 tangent x terms on the top, 1 minus tangent times tangent, which is 1 minus tangent squared. The tangent 2x, we don't use that a lot. Because if we know sine of an angle, and we know cosine of that same angle, thinking back to the quiz, tangent of any angle is sine of that angle over cosine of that angle. So if I want to know what tangent of any angle is, we take sine of that angle divided by cosine of that same angle. So often, if we want to know what tangent of 2x is, where are you going to know sine of 2x and cosine of 2x? If we know sine and cosine, we divide those to get tangent. But in the rare case that we don't have that, it is true that that's equivalent to tangent 2x. Now, real quickly, let's look at the last set of identities for this section. These are on page 511. And then we'll work through a variety of problems involving these identities. So the ones we just looked at were the double angle identities. This set is the half angle identities. So one thing I didn't mention, it depends on what we're given, what we're asked for. But often we'll be given sine of an angle, cosine of an angle, and we'll be looking for sine of twice that angle or cosine of twice that angle. So our input will be cosine and sine of an angle. Our output will be sine or cosine of twice that angle. That's why it's called the double angle identity. If we know this, we can find sine of twice that angle. Where with the half angle identities, if we know cosine of an angle, we can find sine of half that angle, cosine of half that angle, or even tangent of half that angle. So for example, if we know cosine of 30 degrees, if we put that in there, then that allows us to find sine of that input over 2. So sine of 15 degrees. Or if we know sine of 30 degrees, we can put that in and find cosine of 30 over 2, so 15 degrees. So that's why they're called half angle identities. If we have this input, we can find a ratio for half of that angle. Half of that angle. Now, generally speaking, I don't ask you to memorize these. It's important to be aware that these exist. And these are used, I'm pretty sure they're used in Cal 2. They might be used in Cal 1 a little bit. But in Cal 2, they're pretty important. So if you get to there, if you need to take those, then they'll be repeated. We'll remind you of them. But it is at least important to be familiar enough that you recognize, hey, there is an identity that takes the trig ratio for one angle relates it to half of that angle. So let's begin with saying we have sine theta equals 4/5, and let's say that it's in quadrant 2. Now, fortunately, most of y'all have picked up so far on the test that on the back of the first page that was a mistake. Can cosine be negative in the second quadrant? No. So if you haven't taken that yet, I'll go ahead and give you a heads up. The back of the first page, there's a mistake. Remember that in the second quadrant, cosine is negative. So there's a typo. Is it possible for sine to be positive in the second quadrant? Yeah, sine is the y coordinate, so sine is positive. So let's say sine of some angle is 4/5 in the second quadrant. Let's find sine of twice that angle, cosine of twice that angle, tangent of twice that angle, and let's find sine of half that angle. So we don't know what the angle is. I guess theoretically we could find roughly what the angle is with a calculator. But let's say our batteries are dead and we need to solve this problem. So sine of twice an angle is 2 sine of that angle cosine of that angle. So our double angle identity for sine. So we know sine of the original angle. Do we know cosine of that original angle we get? No, but that's something we do have to know. Now there are several different ways we can find cosine of that angle. One way is to say, well, if we're in the second quadrant, we're pointed this way. Sine is y over r. So that's 4, 5, and we can find x. X squared plus y squared equals r squared. So x is -3. So 3, 4, 5 triangle. Other way of figuring it out, we know that sine squared plus cosine squared is always what? 1. So if we know sine, if we take that and square it, add that to cosine squared, that has to be 1. So So 16/25 plus cosine squared has to be 1. If we subtract that from both sides, cosine squared is 1 minus 16/25. Let's see, 1. How many 25ths is 1? 25. So cosine squared is 9/25. How do we get cosine? Square root of both sides. Remember, when we take the square root of both sides, it's technically plus or minus. In the second quadrant, is cosine positive or is it negative? Negative. So cosine is negative, square root of 9, square root of 25. Notice we get the same thing. X over r, negative 3 over 5. So different ways we could get cosine of just theta. We could either draw a triangle, draw our terminal side, and say, well, cosine of that angle is x over r. We know y over r, so x over r is negative 3/5. Or we could use an identity. If we know sine, we can get cosine using the Pythagorean identity. Sine of twice theta. Then we take 2 times sine of theta. Sine of theta is 4/5. Times cosine of theta, which is negative 3/5. 2 times 4 times negative 3, is that negative 24 over 25? That's sine of twice our angle. So sine of our angle is 4/5. Sine of twice that angle is negative 24 or 25. Now we want cosine of twice that angle. We have a variety of identities we can use. The first one was cosine squared minus sine squared. So if we take cosine, remember it's cosine of our original angle squared minus sine of our original angle squared. So cosine of our original angle was negative 3/5. Square that. Sine of our original angle was 4/5. Square that. So what's that? That's 9/25 minus 16/25. So cosine of twice theta is negative 7/25. That makes sense? We just took our identity, cosine 2 theta, and say, well, what is cosine 2 theta equivalent to? This is one thing it's equivalent to. So we replace cosine with what we know it to be, square it, sine with its value, square it, and simplify. Well, if we know sine and cosine of 2 theta, tangent of 2 theta is just sine 2 theta over cosine 2 theta. So negative 24/25 over negative 7/25. If we're dividing by a fraction, that's the same thing as multiplying by the reciprocal. So the 25s cancel. 2 negatives make a positive, 24 on top, 7 on bottom. We took our identities and used them to find a ratio for twice our angle. Now let's ask this question. So sine 2 theta was negative 24/25. Cosine of that same angle is negative 7/25. Tangent of that angle 24/7. What quadrant then is that angle in? So some angle, forget that we call it 2 theta. Some angle has sine as being negative and cosine of that angle is negative. And tangent of that angle is positive. In which quadrant is sine negative and cosine negative? 3. We look at our 4 quadrants. Sine, that's y. Sine is negative down here. Cosine, that's x. Cosine is negative over here. They're both negative in the 3rd quadrant. So whatever our original angle was, twice that angle has to be in the 3rd quadrant. Now, our original angle was in the 2nd quadrant, so it was between those 2 values. So twice that angle, if we double that, all we know to begin with is that twice our angle is somewhere between 180 and 360. If our original angle was in there between 90 and 180, twice that angle, if we double all of that, twice that angle is on one of those. But when we find out, hey, sine and cosine both turn out to be negative, then we can figure out which one of those it is. Cosine's not negative in that one. It is here, and sine is negative there, so that's in the 3rd quadrant. That make a little bit of sense?
You tried it at 180, or the angle, replace 360 with 370, or 2. You know what I'm saying?
So our angle, it turns out that is in the 3rd quadrant, which is between 180 and 270. So once we found out that sine and cosine were both negative, then we can narrow it down. But just with what we were originally told, what quadrant theta was in, we could have gotten an answer in either one of those quadrants, depending on what our angle was. So if our angle was 170, when we doubled that, we would have gotten an angle in the 4th quadrant. If our angle was 100, when we doubled that, we'd have got an angle in the 3rd quadrant. So not knowing our angle, all we knew to begin with, when we doubled it, we were going to get something in one of those quadrants. But once we found out that part, that helped us narrow down, well, which of those 2 is it? So it was in the 3rd. If we want to know what angle theta over 2 is in, if we know that theta is in the 2nd quadrant, then we know it's somewhere between 90 and 180. So if we want an idea of where half of that angle is, half of that angle has to be somewhere between 45 and 90. No matter what our angle is, if we have an angle that's in the 2nd quadrant, when we take half of it, it's going to be somewhere in there. So before we even begin, we know theta over 2 is going to be a first quadrant angle. And that's actually very important because what did I ask? I asked for cosine of theta over 2. The identity for cosine of theta over 2 says that cosine of an angle over 2 is plus or minus the square root of 1 plus cosine x over 2. And I guess my angles need to match. If that's theta, let's call that theta.
Is that still without tangent?
Yes, ma'am. So, this doesn't mean that when we take cosine of half an angle that we're going to get both plus and minus our angle. Because in a single quadrant, is cosine ever both positive and negative in that same quadrant? So cosine is just positive or just negative in any single quadrant. So we have to figure out, okay, for our angle, when we take half of that angle, is our cosine value going to be positive or is it going to be negative? Well, if I tell you that we have a second quadrant angle, which means our angle is between 90 and 180. So I tell you our original angle is between 90 and 180. When we take half of that angle, half of our angle is going to be in what quadrant? What quadrant is theta over 2 going to be in? In which quadrant is 45 to 90 degrees in? 1. 45 to 90, that's in the first quadrant. So that tells us, let's see, in the first quadrant, is cosine positive or negative? Positive. So we're going to have to use the positive sign for our answer. If we would have had a different angle, if we would have had a third quadrant angle, if theta would have been between 180 and 270, then if we wanted cosine of half that angle, then theta over 2 would have been between 90 and 135. Which quadrant is 90 to 135? 2. 90 to 135. So in that quadrant, is cosine positive or negative? In that quadrant, cosine is negative. Remember, on the unit circle, cosine is the x coordinate, so cosine is negative. So if that would have been what we were given, that our theta was in the third quadrant, then when we took theta over 2, cosine would have been negative because that would have been in the second quadrant. So a fair amount to keep up with. So for our problem, let's go back and get cosine of theta over 2. It's going to be positive. It's going to be the square root of 1 plus. And when we were given sine was 4/5 in the second quadrant, we got that cosine was negative 3/5. So for our angle, cosine of our angle is negative 3/5. Several ways we can simplify this. one thing to do is underneath the radical, let's see, on top, 1 plus negative 3/5. So 1 minus 3/5, we need a common denominator. Common denominator of 5, so multiply both of those by 5, so that's 5/5. So on top, we have 5 minus 3, so 2/5. On bottom, we have a 2. If we divide a fraction by a fraction, we keep the first fraction, multiply by the reciprocal of the second fraction. So the square root of 1/5. Remember, if we have a fraction, we take the square root of the numerator and the square root of the denominator separately. So the square root of 1 is 1. 5 is not a perfect square, so it stays under the radical. And if they make you rationalize it, then lastly, we would get square root of 5 over 5. So one of the first main steps, I think they probably do a little bit with cofunction identities first. But then one thing is, how do we relate sine, cosine of an angle to sine, cosine of twice that angle or half that angle? So that's what we did there. Something else that you might be asked to do is to find sine of a particular angle using half angle identity. So they might say use a half angle identity to evaluate exactly what sine of 15 degrees is. So if they say exactly, that's going to be a key. Hey, we're probably going to have to relate this to a reference angle. So remember, sine of an angle over 2 is either plus or minus the square root of 1 minus cosine of an angle over 2. So if half of our angle is 15 degrees, if our half angle is 15 degrees, then what's the full angle? What? I think you said 30. So if theta over 2 is 15, then the full angle theta is 30. So if we want sine of 15 degrees, we have to use cosine of 30 degrees to figure that out. First of all, at 15 degrees, the sine is going to be positive or negative? Positive. This is the first quadrant. 15 degrees is in the first quadrant. Everything's positive in the first quadrant. So we can drop the negative. Again, notice this angle is half that one. 15 is half 30. So to find exactly what sine of 15 degrees is, it's the square root of 1 minus, let's see, what is cosine of 30 degrees? You can either draw the triangle, or if we look at 30 degrees, what's our x coordinate at 30 degrees?
Square root of 3 over 2 and 1/2.
Yep. So which one of those is cosine? Square root of 3 over 2. Do y'all know how I got that? So out of our standard angle, or our standard, angles, all of those one, out of those three, is that the farthest to the right, the least to the right, or the one in the middle? Out of those three, is that the farthest to the right, or the least to the right? It's the farthest to the right. So that means the x value there has to be the largest. Because that's the farthest. It takes farther to go this far to the right than it does this far to the right. So that means the x coordinate has to be the largest one. Which of those is the largest one? The square root of 3 over 2. That's the lowest of those 3 points. So it has to have the y value that's the smallest. To get to here, we go up less than if we go up to there or up to there. So to go up to there, that's the smallest, so 1/8. So without even drawing our triangle, cosine and sine, so at 30 degrees, we know cosine is square root of 3 over 2. That's just a faster way than having to draw your triangle, especially when we get into second, third, and fourth quadrant angles. If you look at how far to the right or left, how far up or down it is, fill it in with one of those 3. Yeah. Did you have Miss Allen or Miss Phillips?
Miss Phillips, I had her for like 3 weeks.
And then she retired.
And then she retired. And she had to come back for 2 days because she didn't have the right amount of hours.
Oh no.
And then made her come back for 2 days.
That's funny. I imagine y'all probably didn't do a lot those 2 days, did you?
No. She was just ready for her days, you know.
There are a couple ways we can simplify this complex fraction. One way is to, instead of dividing by 2, multiplying by 1/2. Let me remind you the other way. If we look at each of these as individual fractions, this has a denominator of 1, 1, and 2. If we have denominators of 1, 1, and 2, what would a common denominator be? 2. Let's multiply top and bottom by 2. If we multiply the top by 2, both of those get multiplied by 2. So 1 times 2. If we multiply that times 2, the 2 on bottom, that 2 cancel. On bottom, 2 times 2 is 4. If we have a fraction, we take the square root of the top, which that's not a perfect square. On bottom, the square root of 4 is 2. So that's an exact value for sine of 15 degrees. Now you'd have gotten the same thing if you would have combined those into a single fraction and then multiply it times 1/2. Got the same thing. But it is good to keep in mind different ways of simplifying complex fractions. Because depending on how messy they are, a lot of times this is actually a better way to do it. All right. Let's stop there. For homework, you'll have an opportunity to practice a variety of those. The biggest thing is getting familiar, how do I use each of those different identities? So tomorrow, co-function identities, sum and difference identities, and double angle identities. Be ready to take a quiz on those.
We're done, yeah. Hold on.